This video is an introduction to chi-square test. In this example, we are going to test to see if a die is fair. A gambler is accused of using a loaded die, but he pleads innocent. We will check if the die used by the gambler is fair or not. Each throw can be classified into one of 6 categories depending on the face, values 1, 2, 3, 4, 5, or 6 for a 6-sided die. In scenarios when there are more than 2 categories, statisticians use the chi-square test rather than the z-test. The z-test would be appropriate for a question about the average roll from a die, but not a question comparing 6 categories. So in this case, the chi-square test is the appropriate test. We're going to compare each of these 6 die faces. Here's a record of the last 60 throws of the die, and we'll be counting up the different faces in the table below. So if the gambler is innocent, how many times do you expect each number to turn up? Explain your reasoning. So if the die is fair, then we expect p equals 1 out of 6 to be the proportion for each face. We've got 60 throws here, so we can say n equals 60 throws. And then we know we can find the expected value by taking the number and multiplying it by the probability of each face coming up. So 60 times 1 out of 6 is 10 times for each face. So if this is a fair die, we expect each face to come up 10 times. Now we know this is a random event, rolling a die, and we know from when we have tossed coins or rolled dice in the past that we expect some variation due to chance with random events. So it might not be that the faces come up exactly 10 times if the die is fair, but if the die is fair, we don't expect our results to be too far from 10 times for each face. So we're going to make a table to compare the observed frequency and the expected frequency for the die. The observed frequency counts the number of times each face value comes up, and the expected frequency counts how many times each face should come up according to the model for a fair die. So we've already calculated the expected value, 10, so for each face we've got 10, so that's our expected frequency. And then the observed frequency comes from counting the values in the list above. So you go through the list and cross off each time a 1 comes up, you should get 4 times. Then go through, cross off each time a 2 comes up, you should get 6 times. Cross off each time a 3 comes up in that list and you get 17 times. Cross off each time a 4 comes up in that list and you get 16 times. Cross off each time a 5 comes up and you get 8 times. Cross off each time a 6 comes up and you get 9 times. So the total of the observed frequency is 60 also because there were 60 rolls. So now we want to do some analysis on the table. Does it look like the observed frequencies are close to the expected frequencies or not? And until we start doing some calculations, we're just estimating based on what we see in the table, but it does look to me that the face values 1 and 2 are pretty low compared to 10, and the rolls, the observed frequency for face values 3 and 4, are a bit high compared to 10. So my answer to question C, judging from your work in part B, is the table fair? If not, which face values come up too often, is to say that the table does not seem to represent a fair die. Faces 1 and 2 turn up less often than they should. Faces 3 and 4 turn up more often than they should. But we still need to do some calculations to see if this is a fair observation or if the difference is just due to chance. We can't draw any conclusions yet. Since there are many lines in the table, there's a high probability that at least one of them will look suspicious, even if the die is fair. The chi-square statistic combines all the differences from the 6 lines in the table by measuring how far the frequency of each face value is from 10, the expected value. So this is the general formula. We say chi-square equals the sum, that sigma, capital sigma in Greek tells us to add up all of our calculations. So it's going to be the sum of this fraction. On the top of the fraction, we're going to do the observed value minus the expected value. And then we're going to square that. So recall that we square numbers in statistics to convert from negative to positive values. We do the same operation in the standard deviation calculation. And then we're going to divide by what we expected, the expected value. So here is the chi-square statistic for our die roll. So remember the face for 1s came up 4 times. So this first calculation is to say 4 minus 10, which will give us a negative 6. And then we square that. So it's a -6 because our face value of 4 was 6 below what we expected. We don't want to deal with the negative, so that's why we square the value here. We're concerned about the absolute distance, so squaring can take care of the negatives, and we'll see overall how far away the values are. And then we divide by 10. The same thing for the face value of 2 that came up 6 times, and so on. So you can see each of these first values under the observed part of the calculation corresponds with what we observe for those face counts. And then our total, because we have the same denominator 10, this is a pretty easy calculation to do by hand. Our denominator is going to stay 10, and then we can add up the numerator totals. And so the numerator totals are 142. And then our final calculation is 142 divided by 10, or 14.2. So this is called the chi-square statistic in part because they're squaring in our formula. And then some statistician at some point used the Greek letter chi for the formula, probably because chi wasn't used for anything else in statistics. I don't think there's any special reason that this is called chi-square, but the square part is because we square in the formula. So with chi-square testing, when the observed frequency is far from the expected frequency, we're going to get a large sum here when we add up all these pieces because each of these observations overall are further away when we total them up. And then when the observed frequency is close to the expected frequency, the sum should be pretty small. If you look over at faces 5 and 6, those last two calculations in the sum, those were both pretty close to 10. We got 8 and 9 faces respectively. And so those parts of the sum are pretty small. Overall, we got a pretty big chi-square value here because of the influence from the 1s and 2 faces and the 3 and 4 faces. So our chi-square statistic is 14.2. We need to find out if that's a reasonable statistic or not. So to find out if the chi-square statistic is reasonable, we need to know the chance of getting a chi-square statistic of 14.2 or more. So in StatCrunch, we are going to use the StatCrunch calculator for chi-square, just like how we have the normal calculator for the normal curve. And then we'll see on the next page how we can use a chi-square table in the same way that we have a table for the normal curve if we don't have the StatCrunch available for us. So let's head into StatCrunch and see how the chi-square calculator works. We're going to go to Stat Calculators and choose chi-square. So I'm going to open a blank StatCrunch. And then I will go to Stat Calculators, just like where I go for the normal calculator, except we're going to choose the chi-square curve right here. And so you can see the chi-square curve is a right tail curve. It is not symmetric. It's got a curve to it. And then depending on the degrees of freedom, the curve is going to be skewed more or less. So the degrees of freedom are the total rows in the table or the total variable options minus 1. So it's the number of values in chi-squared minus 1. So in this case, with the die, we had 6 possible values. So if we subtract 1, we have 5 for the degrees of freedom. And then we want to see what's the chance of getting a chi-square value greater than or equal to 14.2. And then if we hit compute, we see here's our red area out in the tail. And this p-value is relatively small. It's less than 5%. It is 0.0144 if we round to 4 decimal places. So I recorded that here. The p-value is less than alpha equals 0.05 significance level. So what kind of conclusions can we make about that? If the die is fair, results like this would be considered unusual. So we would conclude that the gambler is guilty of using a loaded die based on the fact that our p-value is less than that 0.05 significance level. If we write out the hypotheses, this would be a scenario where we're rejecting the null hypothesis and we're accepting that the die is not fair. There is enough evidence. So here are some general chi-square graphs. You can see over on the right, we see if the degrees of freedom are 5. That would mean you have 6 different chi-square values, like the 6 faces of the die. That the curve is a little flatter than if there are 11 degrees of freedom. So you can head into the chi-square calculator in StatCrunch and adjust things if you want. If you wanted to change this to say 10, you can see how the curve changes a little bit and there's a bit more area there. So the shape of the curve depends on how many different chi-square values, how many different categories we're counting. So in order to calculate the chi-square, we need to know the degrees of freedom, which is always going to be the number of values minus 1. So in this case, we had 6 die faces. Take away 1, we have 5 degrees of freedom. That reasoning is because if you knew the first 5 values, you could figure out the last value, knowing what the sum of the die or the sum of whatever your variable is. So we say only 5 of those variables are free to move around. In physics, they talk about them as pivot points very often. Okay, so here's the old-fashioned way of finding the chi-square value. So if we didn't have StatCrunch, we would use a table like this. And in our table, we come down to 5 degrees of freedom row. So I highlighted the 5 here. And then we would look for where our chi-square value is. So we would come over in the table until we find where 14.2 chi-square value would lie. So that's over between 11.07 and 15.09. And then if we look up to the top of the table, we see there's our probability of getting a larger value of chi-squared. So we are somewhere between 0.05 and 0.01 probability from using the table. So you would use the table if you were on the bus or had a power failure. Otherwise, the chi-square calculator in StatCrunch is much preferred for us. So the chi-square value is 14.2 and 5 degrees of freedom. Using the table, we conclude that the p-value is between 0.05 and 0.01. And StatCrunch gave us the exact value of 0.0144. So definitely below that 5% significance level. So we are thinking that the gambler is guilty of using a loaded die.